I want to pick up where we, not exactly where we left off. I want to do a little bit of a review of where we've been and put in a more systematic way some of the extensions of the kinetic theory that we have to make, of the simplest kinetic theory that we first studied, the extensions that have to be made to that to make it more realistic in order to apply to real physical situations. So that's the first thing I'll do. And then I'm going to try to indicate the relationship between the dense kinetic theory and a simpler phenomenological rheology that you've heard something about in earlier lectures, and that's very popular and successful in simple situations. And then finally, I want to take the extensions to create more realism in the kinetic theory and apply that to two physical experiments. So here's a review of where we started, really. We focused on a kinetic theory for smooth, nearly elastic spheres, and I said that applicability of that theory was going to be restricted between 30% and 49% in volume fractions, and we saw some evidence of why that should be the case, but I'll return to that. And the constitutive relations of that dense kinetic theory for smooth, nearly elastic spheres were essentially identical to that of a compressible, viscous, heat-conducting gas or liquid. Okay, so we have analogies in mind for the flow behavior of this collisional dense gas of nearly elastic spheres. And there's the density dependence or the volume fraction dependence of the theory is pretty much governed by a function of volume fraction that's related to the radial distribution function that was mentioned earlier today, in that the density, that function of the volume fraction or density appears in all of the transport coefficients. And then there are numerical factors that also enter, and in the simplest kinetic theory that we considered, we didn't have these additional terms here. These additional terms are contributed when the Boltzmann equation or solutions to the Boltzmann equation are employed in order to derive a kinetic theory for these dense elastic, nearly elastic flows. Okay, so that's more or less the structure of the simplest theory, let's say embellished by some contributions from solutions of the Boltzmann equation. And then we saw that for volume fractions greater than 49% and below dense random packing, we could obtain a more appropriate theory, a theory that at least predicted the qualitative features of inclined flows by introducing another length scale only in the rate of collisional dissipation. And that length scale was determined roughly by a relationship that balanced the orienting effect of the shearing with the randomizing effect of the collisions. And there's another function of volume fraction that intruded between the two, and this function of volume fraction is determined in numerical simulations of shearing flows. Okay, so that's pretty much where we are right now. But now I'd like to motivate various extensions to more complicated interactions between spheres. Okay, so we want to increase the dissipation, we want to incorporate friction, and we want to extend things to volume fractions all the way up to 64%. And some of this I've mentioned in the past, but now I want to give a somewhat more systematic presentation of these extensions. Okay, So if we solve the Boltzmann equation for more dissipative spheres, not nearly elastic spheres, so now we abandon the assumption that the coefficient of restitution is near 1. In that event, these simple coefficients that we were talking about for nearly elastic spheres incorporate a dependence on the coefficient of restitution. Okay, and of course, when the coefficient of restitution nears 1, we recover the simpler forms. But if we're going to apply the theory to more dissipative collisions, these are the forms of the coefficients J and M that we'll have to employ. Okay, so that's one thing. And let's see. And here's something else that I mentioned, but I'll be a little more systematic. So the idea is we've been dealing with smooth spheres, that is frictionless spheres, but realistically, we're dealing with systems of particles that interact through friction. So the presence of friction means we have to take into account the rotational degrees of freedom of our particles. So the frictional interaction involves sliding, frictional sliding, for which there's a coefficient of sliding friction that we'll use to characterize it, and it involves a coefficient of tangential restitution. That's the analog of the usual normal coefficient of restitution that says something about how much velocity, how much angular velocity is returned in a collision in which there is no frictional sliding. And the thing about a frictional collision is two things can happen during a frictional collision. There can be tangential restitution if the particles are sticking together, or there can be sliding during the course of the collisions if the particles are not. And whether or not the particles are sticking in a collision or sliding in a collision depends upon the relative magnitude of the tangential impulse to the normal impulse, in the same way that Coulomb friction depends upon the ratio of the tangential force to the normal force. If the ratio is too small, no sliding will occur. If the ratio is at the value of the friction coefficient, there will be sliding. Okay, so that it's relatively easy to incorporate, so that, as I said earlier, the way we take into account the presence of these rotational degrees of freedom is to try to understand the rate at which energy is lost, is lost from the translational energy to the rotational energy through sliding friction and through the transfer of translational fluctuations to rotational fluctuations. And if we solve if we solve the energy balance in a homogeneous, steady, simple shearing flow, we can use the information that we gain from studying those transfers, characterizing those transfers, and introduce an effective coefficient of restitution that gives the influence of those rotational modes on the translational modes. Then in doing this, we spare ourselves having to solve a balance equation for angular momentum and a balance equation for the rotational energy. And there are two limits. The one limit is when, in this cloud of colliding gases, every collision involves frictional sliding through the entire collision. That's one extreme. Another extreme, and that's when the tangential impulse dominates the normal impulse. On the other hand, when the normal impulse dominates the tangential impulse, every particle in every collision is sticking, and in that limiting case, only involves the tangential coefficient of restitution. So typical particle typical particle collisions are rather dissipative and involve coefficients of friction that are on the order of 0.3. And so that puts us closer to this all-sticking regime. But in fact, we can interpolate between these two regimes to deal with the general case where in a typical collision, both sticking and restitution occurs. So the general collision involves both. Okay, so there's a way of introducing an effective coefficient of restitution that takes into account the presence of friction.
So when we model a collision in simulations, if we use those effective coefficients of restitution, we don't need to incorporate the tangential damper and
Well, these are not ever used in simulations, because in the simulations it's relatively easy to incorporate both the tangential and the normal forces and frictional sliding. So there's a typical 3-parameter model that's employed in most simulations that you implement. It's really in the formulation of theory that you want to use an effective coefficient of restitution in order to avoid using those additional balance equations and the need to determine what boundary conditions might apply to those additional balance equations. So this is simply a convenience, if you like, for the theoretician, for the modeler. So we can make use of the balance of momentum for the translation and the balance of energy for the translational degrees of freedom only. Okay. All right, so that's one thing. Another thing is that if the particles are frictional, then the collisional motion in a shearing flow is observed to stop before random packing is achieved. And this stopping of the collisional motion is called jamming. And what that means is that in this characteristic volume fraction dependence of the constitutive relations, rather than having this singularity occur at random close packing, we have it occur at a volume fraction that's somewhat less than random close packing, typically on the order of 0.6. Okay, so that may not seem like a very large modification, but I mean it's important to know when the collisional theory stops, at what volume fraction something else is taking place.
Which you take as a given input, a phenomenological input.
Yeah, that's at the moment. That is, we have information about how that critical volume fraction depends upon friction, but it's purely from simulations. Okay, and finally we talked about this last time. We want to take into account velocity correlations, or the breakdown of this assumption of molecular chaos. So in that case we're able to introduce. So this is kind of another minimal modification of the theory. So we've made one modification of the theory by employing an effective coefficient of restitution. Now it appears as if the velocity correlations and their influence on the theory can be taken into account if, in the rate of dissipation, we introduce another length scale. And that length scale, as I said earlier, is determined by a competition between ordering and randomness introduced by collisions. And numerical simulations have indicated that, in fact, this length scale is not singular where the collisional theory fails, but in fact this length scale is remains singular at random close packing. Now, I'm not going to make too much of a distinction in what I say between the fact that this function g is singular at something other than random close packing, while this function f is singular at another point. But it does have consequences as we try to push the collisional theory to higher and higher volume fractions. Okay. And let's see. Oh, and if we do that and use the fact that the simulations indicate to us that the diffusion of temperature is negligible in these flows that have a volume fraction between 49% and 64%, then we can come up with a relatively simple determination of the stress ratio in a steady inclined flow, for example, or a steady homogeneous shearing flow, and that stress ratio inherits the volume fraction dependence from the length scale. And that's a crucial indicator that we have a more appropriate theory, because once again, numerical simulations tell us that the prediction of the simplest kinetic theory, that the stress ratio is constant. Oh, I'm sorry. Now here I'm using phi as volume fraction. This is volume fraction nu. That the simplest theory says that the stress ratio is essentially constant over this range of volume fractions leading up to random close packing, but the numerical simulations are indicating that in fact there is a substantial decrease in the stress ratio as the volume fraction is increased. Now, there's not exact quantitative agreement between all of these numerical simulations, because some of these numerical simulations are done for hard particles and others are done for particles with various degrees of stiffness. So the stiffness ranges from 10 to the 5 to 10 to the 7. But this extended kinetic theory we're talking about follows that branch, which is also followed by the hard particle simulations. And here's an example. Let's see. So we're talking about coefficients of restitution of 0.7 everywhere here. Coefficients of sliding friction, well, some frictionless, some a coefficient of sliding friction of 0.1, others of coefficient of sliding friction of 0.5. So we've converted all of this information into effective coefficients of friction.
What kind of deformation is this problem? Is it inclined plane or?
Well, this is simple shearing. This is periodic cell simple shearing. Okay, let's see. So that's I wanted to touch upon all these aspects again in a little more systematic way. Okay, so now let's talk about the relationship between this kinetic theory, this extended kinetic theory, extended to include the additional length scale, and a rheology originally for steady, homogeneous shearing flow that has been put forward by French researchers. Let's see. So what we find is that in the kinetic theory, the extended kinetic theory, we had an expression for the stress ratio that depends upon the effective values of coefficients. This function j, which is now a far more elaborate function of coefficient of restitution, effective coefficient of restitution, and this function f that is involved in the determination of the length scale. So what that gives us is stress ratio as a function of volume fraction. Okay, that's fine. And the parameter I and this ratio, I have to beg your indulgence now, because now I'm using mu to denote this ratio. Okay? So forget that mu stands for stood for sliding friction in the past. Now mu, from this point, mu is the mu of the mu I rheology, which is the ratio of the shear stress to the pressure. Okay, so that's the mu, and the I is a combination of the particle diameter times the shear rate divided by the square root of the pressure upon the mass density. And that we can determine from the constitutive relations of this extended kinetic theory to behave upon the volume fraction in two ways, through F and through G. But the point is that then both of these quantities depend upon only the parameter nu given a material and a coefficient or an effective coefficient of restitution epsilon. So we can imagine eliminating the volume fraction between them and obtain mu as a function of I over the range of volume fraction. And I just point out that what we've done here is we've eliminated in the kinetic theory, we've eliminated the granular temperature and expressed everything in terms of the strain rate, the shear stress, and the pressure. And in fact, in the mu I rheology, there's no mention of any measure of velocity fluctuations. It's phrased entirely in terms of shear stress, pressure, strain rate, and the density. And the advantage of the mu I rheology is that it's extremely easy to employ in situations where you know in advance how the pressure varies. So in the inclined flow, for example, the pressure increases linearly as you go from the top of the flow to the base of the flow. And in many other granular flows, you do have that information in a very natural way. If you don't know the variation of the pressure, then it's somewhat more complicated to attempt to determine the quantities that govern the behavior of the flow. Okay, and now in the next slide, I'll just show you what results from eliminating the volume fraction between these two relations. And maybe I should emphasize that we can, let's say, emulate, or we can place into context the mu I rheology only for collisional flows. And our ability to predict using the constitutive relations we have is limited. So let's imagine we're sharing a dense granular gas in some kind of a cell. And we saw that this measure of L is a rough measure, perhaps, of the dimension of a cluster size that forms in the shearing flow. Okay, well that's fine. So capturing that length scale associated with the clusters or correlated collisions gives us predictive capabilities up to the point where these clusters span the cell. And now the clusters, of course, are not permanent features of the flow. They're breaking up and reforming, breaking up and reforming, but typically they're oriented at 135 degrees to the flow direction. So they maintain an orientation, although the members of individual clusters are changing as the material is sheared. But the point is, as soon as this cluster spans the cell, then there's another mechanism available for transferring force, let's say, from the top cell to the bottom cell. And if these particles are interacting, let's say, in a compliant way, that is, if there's some stiffness that is not infinite, there's elastic transmission of force across the cell. So as soon as we have that mechanism as soon as we have that mechanism for force transfer and momentum transfer present, we lose our predictive value. Okay? However, the mu-I rheology seems to work rather well all the way up to the point where the flow, well, and I would say a flow continues. A flow that is shearing can be maintained here, and the resistance to that shearing then is the mixture between collisional exchanges and the force and momentum transferred by the force chains. And the mu-I rheology seems to do pretty well in describing that until the flow stops, until flow is impossible. Yeah.
This is kind of not directly related to kinetic theory, but the mu-I rheology that you mentioned, how different is it from what you would obtain from plasticity theory with some yield, with some flow function?
Well, it is a type of viscoplasticity theory, and I mean, when you say how different is it, if you were to write down a phenomenological theory using, let's say, the dimensional parameters that are present in a typical problem, you would probably be led to something like the mu-I rheology.
So I guess what was so kind of original then in the mu-I rheology, I've never quite been able to pinpoint. Is it the fact that the mu dependent on inertial number, was that what was novel in it?
So let me say this, that a parameter that appears again and again in the kinetic theory is that parameter. And we saw that
That's diameter of the
yeah, sigma, I'm using sigma as a diameter. I think later you'll see I revert to D. Apologize for that. Okay, so people who let's say worked on kinetic theory, they're accustomed to seeing this as a parameter. But if you use this as a parameter in dense shearing flows, it doesn't collapse the data. Okay, the contribution of the mu-I rheology, I think, was to recognize, either through a careful study of the simulations or appropriate intuition, that the quantity you want to scale the shear rate involves not simply the temperature, but it involves a function of volume fraction times the temperature that's represented by the ratio of the pressure on the density. So I'm not I mean, and this you could also argue that you can come upon this dimensionally, but this is as good a dimensional combination as the other from purely dimensional analysis.
and for gases P by rho is P is rho.
For a dilute gas, so we're interested in dense flows. That's what the mu-I rheology works for. So introducing this function of volume fraction and temperature then allows the data to be collapsed. Okay, so that really is a contribution. I mean, it doesn't seem like so much, but in fact it's rather profound. Okay. All right, so here are typical predictions. So here's this is for an effective coefficient of restitution of 0.6. Okay, so that I should say, so why do we bother, with kinetic theory when we have a mu-I rheology? And one answer might be is that in the kinetic theory there's one parameter. Well, I should be careful. This function is determined by numerical simulation, but apart from that, there's one parameter. That's this effective coefficient of restitution that depends upon the normal coefficient, tangential coefficient, and coefficient of sliding friction, but you can measure these guys independently in experiments. So there is, let's say, there's definite information that can be employed in order, when you place the mu-I rheology in the context of the kinetic theory. The mu-I rheology depends upon one or more, as many as 3 coefficients that have to be determined perhaps by fitting 2 experiments. And these coefficients will typically depend upon the geometry of the experiment that you're carrying out. Whether you're shearing without rotation, whether you're shearing with rotation, the mu-I rheology can describe both, but they can't describe those 2 different situations with the same phenomenological parameters.
One more question about the mu-I rheology. I'm sorry.
That's fine.
Is that the pressure that they use in the inertial parameter usually has to be specified? I haven't seen any examples where they have computed it as part of the problem. For example, in inclined flow, P is rho gx.
Well, so let's see. So the original mu-I rheology didn't have a relationship between the volume fraction and the stress ratio. But if you have a relationship between the volume fraction and the stress ratio, then you can phrase the mu-I rheology as a more traditional set of constitutive relations. But I've never seen a problem. I'm sure people have solved problems of the type that you're suggesting, but I just haven't seen those solutions.
The reason I was asking is because it was very unusual for me to see the pressure inside the coefficient.
Well, I would say from the standpoint of people who work in rheology, these really aren't, the relations of the mu-I rheology don't appear to be constitutive relations.
Exactly, that was the,
Yeah.
Yes, so it is funny. It's not a given input in some sense. It's what would you like to determine from many problems. Would be the-
Yeah, absolutely. But what I'm saying, in the original mu-I rheology, you couldn't, because they weren't so worried about volume fraction and stress ratio. But they later introduced a second relation, and that means you can unwind the mu-I rheology and have constitutive equations separately for the shear stress and the pressure in terms of the strain rate. Okay, so you can do it. But in effect, that you're losing the utility, I think. The thing about the mu-I rheology, I think, that is so nice is that if you know the pressure,
then it's very
Okay, so so what I'm showing here, then so here I show the stress ratio versus this inertial parameter over a range of inertial parameters, and this is nothing crazy about that relationship. And similarly, now here is their relationship for the volume fraction. That's what that's supposed to be, versus the inertial parameter, and that's monotonically decreasing. So here are the 2 relations of the theory, but this predicted using the kinetic theory. Okay, so that's one thing I wanted to say. And now more recently, there have been efforts by people who are using the mu-I rheology to deal with flows that are inhomogeneous. So the mu-I rheology was originally introduced for homogeneous, steady shearing flows, but most flows involve the influence of a boundary or 2. So the efforts have been made to extend the mu-I rheology to deal with those kinds of flows. So I remind you that in the kinetic theory, we have an energy balance. So I'm looking at a simple one-dimensional situation. So suppose we're shearing between bumpy plane boundaries. So I'm trying to show now spheres rigidly attached to the boundary, and then we have spheres in the interior. So, and the only direction then in a fully developed flow in which things are changing in the vertical direction. So here we have an energy balance in the kinetic theory, and we have constitutive relations for the energy flux, constitutive relations for the shear stress, and for the rate of collisional dissipation. And we can naturally then deal with the flow in the interior. And in addition, we also have talked about boundary conditions. Boundary conditions that are obtained in roughly the same way as we obtained our constitutive relations by considering the exchange in momentum in a collision between a flow particle and a wall particle, and the exchange of energy in a collision between a flow particle and a wall particle. And the result of these considerations give us an expression for the slip velocity at the wall in terms of a coefficient that depends upon the wall bumpiness and other parameters that appear in the theory, not necessarily parameters, fields, the square root of the granular temperature and the stress ratio. And also we have an expression for the transfer of energy at the boundary that tells us about the magnitude of the flux of fluctuation energy as being determined as the difference between the working of the shear stress, and there shouldn't be a derivative there. This is the working of the shear stress through the slip velocity minus the rate at which collisions dissipate energy at the boundary. So we have relatively sophisticated, I would say, boundary conditions that apply at both rigid, bumpy boundaries and at boundaries that I call erodible, and that's when the flow is not over a rigid boundary but on a bed of similar particles. Well, similar, and let's say it can be a bed of spherical particles, perhaps not of the same diameter. It's easiest if it's the same particles.
Other question, what do you mean by inhomogeneous sharing? The picture you drew.
What? Yeah. All right. So I'm sorry. So let's say the boundaries are identical and there's no gravity. Then, as a consequence, I got to be a little bit careful here. Let me show some slip at the boundary. I mean, a slip is generic for the granular materials. So what I've shown here then is the fact that collisions between particles in the interior of the flow transfer momentum in a way different from the collisions between an interior particle and a wall particle, means that the transfer of momentum at the boundary is different from the transfer of momentum in the interior, and that means that the velocity profile is not uniform or even linear across the cell. And similarly for the temperature profile, if Q is positive, the fact that there's a slip velocity is driving particles into collisions at the wall, which creates fluctuation energy at the wall, and that creates inhomogeneities in the temperature profile across the cell. So that's what I mean by inhomogeneous flows. Steady, but inhomogeneous. Okay, and now I want to relate, let's say, this activity in the context of the kinetic theory to the mu-I rheology. So the extensions of the mu-I rheology to inhomogeneous systems have been made principally by Ken Cameron and his students and colleagues, and the way that we can recover the kinds of equations, or the single equation really that he's been focused on, is once again to eliminate, to use the algebraic energy balance of the kinetic theory to eliminate the square root of the temperature in favor of the strain rate. And these known functions of effective coefficient of restitution on one hand and volume fraction on the other. And then use this relation to eliminate the temperature from the shear stress and the rate of collisional dissipation. And if we do that, then the energy balance can be phrased not as an equation for temperature, but a second order equation for the strain rate with coefficients depending only on volume fraction. Okay, and that's exactly the structure of the Cameron theories that have been put forward recently. They deal with a single equation, second order equation for the velocity.
If I may say something, so in other words, if I take the normal kinetic theory-like arguments for granular flows with the energy balance, and then just unwrap the energy balance with a T equal to statistical laws, I recover the fluidization kind of theory of Cameron.
Yes. Yeah, I would say with the additional advantages that, well, Cameron will typically,
This energy balance doesn't need a second order. I'm sorry, I'm thinking out.
Yeah.
Sorry, Jim.
so they typically require a priori specifications of the shear stress or the pressure. They have to specify them as functions of position for the boundary value problems that they're dealing with. And they're rather uncertain about the nature of their boundary conditions. So what I'm suggesting is that,
Did you get the length scale? I'm sorry.
pardon me, go ahead.
Did the length scale come out of that too, from the temperature? So does the length scale that emerge with the fluidization length and so on come out of this then? Yeah?
Yes, yeah.
Sorry, what is the fluidization length? Capital length.
No, the fluidization length is something different. It's a length scale that's inherent to the, well, the fluidization length is related to our length L. Yes, it's singular in the same way. Yes, so the short answer is yes. And it's the length that we've been looking at. Okay, and we have, you know, by virtue of the derivation of our boundary conditions, oops, where am I? So we have pretty good boundary conditions. So there's or viewed in another way, we can help Cameron inform his phenomenology by making use of the relationship between the two theories.
How exactly was it extended? What was the extension?
So the extension I'm talking about is the introduction of this additional length scale, L, in the rate of collisional dissipation.
In mu I, but you say extension of the mu I rheology to inhomogeneous.
Well, so the extension by Cameron is to inhomogeneous flows.
So this is just a different boundary value problem. You keep the constitutive law the same, but you apply it to a more.
Well, the original mu I rheology didn't deal with boundary value problems. It just was as, homogeneous shearing. I mean, people have attempted to move away from that and apply it locally and inhomogeneous flows, but Cameron has really been the only person that has attempted to phrase boundary value problems in his extension of the mu I rheology. Okay. Yeah, so the point is we can understand the relationship between the kinetic theory extended using this length scale and the original mu I. And now we can understand we can place into context Cameron's work on BVPs in the context of the kinetic theory BVPs. Okay, so I mean, otherwise the Cameron work is a little bit mysterious, and it always does beg the question: is well, how might this be related to a more microscopic picture of the granular flow?
And they will specify the slip length separately, or is it computed?
They put it in as a singularity. I mean, we put it in as a singularity. That is what corresponds to their slip length is this guy. Okay, but they introduce that as part of their phenomenology.
I was wondering what the boundary conditions.
For them? Well, I mean, they'll typically take a no-slip condition at the boundary, for example, and maybe no heat flux at whatever boundary they're dealing with, yeah. So the kinds, well, they've dealt with a variety of boundary conditions, but they're taking the simplest boundary conditions you might think of and employing them. Well, I said no heat flux. They don't. Heat flux doesn't have a role in their theory, so they'll typically take a no-slip condition for the. Oh, wait a second. So they have a second-order differential equation. So they need more. They need two boundary conditions there, and the second boundary condition may be something they make up.
I was looking at that picture and wondering what the free surface would be.
Well, typically, well, that's another story. Okay, that's the next chapter. But at free surface, they're not dealing too often with free surfaces. But at free surfaces, it's natural to assume the shear stress is zero and the energy flux is zero in the kinetic theory. Now, I mean, there are refinements to that. And so typically at a free surface, because you've got collisions of the particles just below what you might call the top of the surface, you have particles moving in ballistic trajectories. That is, they move without experiencing collision until they come back to the top of the flow. But you can take that momentum transfer into account as well.
That's in kinetic theory. I was hung up on the Cameron new ideology.
I don't know that he's ever solved a free boundary value problem.
I thought he did, but
I think he has.
Think so?
There's a tank that the rotating tank with the profile that goes up, but I think it's just no shear. So I think it somehow it comes out without difficulty, that kind of boundary for the free surface one.
He might assume that the velocity derivative is zero at the free surface, and that's equivalent to shear stress vanishing at the free surface. Okay.
There don't seem to be problems with free surfaces. There's other places there are steep gradients, so that's probably
I think that's true, yeah.
as long as you can certainly map them out all.
Okay, so now, any questions? Now I'm going to look at a couple physical experiments and show how the theory can be employed in order to attempt to make predictions in the context of the physics. And I'm going to have to warn you again. Let's see. So I've taken the remainder of talk from older work where I might call the diameter d. All right. We'll see. Okay. So here are physical experiments that were carried out by the French group. And what's the story here? So these guys are looking, so they have a hopper, and they can control the rate at which grains are released from the hopper into a cell, which has a width W that they're going to change between different realization of the experiments. So this flow is onto a bed of particles. The bed is maintained by having a plate at the end of the cell, and then the flow moves over the surface of the bed, and when the flow rate of the hopper is matched in a sense with the width of the chute, they get over at least a substantial range of the flow, a steady, fully developed, that is rather uniform flow, variations only across the profile. Okay, is the situation clear? So, and what they measure then is the rate at which material is flowing, mass flow rate per unit width of the cell, normalized, made dimensionless in an appropriate way, and the tangent of the angle of inclination of the free surface of the flow. Okay? And the data that they obtain is different depending upon the width of the cell. Or that is, it depends differently upon the angle of inclination depending upon what the width of the cell is. So here, if the width of the cell is the smallest that they employed, 19 particle diameters, then as they change the angle of inclination, this is the data that they obtain. Here is what? I can't see. This is 57. I don't know what exactly what this is. So 57 diameters. Here is the relationship between the angle of inclination and the normalized mass flow rate, etc. Okay, so the question is,
So the narrower it is, the lower the flow rate is.
the narrower, no. So let's see, the narrow, so here we are at a, let's compare so here, this is narrower than this, so that, okay, yeah, I think you're right. At the given angle of inclination, greater flow rate, greater width. Yeah. Okay, so that's the data. And I should say, you know, we're not trying to predict here profiles of the velocity through the depth of the flow. We're not trying to provide volume fraction profiles. It's pretty crude. We're trying to predict how much stuff gets down given an angle of inclination and given a thickness. Okay, so it's, you might say it's not a very rigorous test of the theory, but of necessity we ought to be able to do something crude before we do something more refined. Okay, and what we're going to do is we're going to use this algebraic theory. So remember what we said is that in the inclined flows, what we saw was that if we're looking at a profile of volume fraction across this inclined flow, we had something that looked kind of like this. That is, over the majority of the flow, the volume fraction is uniform. It's only near the wall and near the free surface that there are substantial gradients. So, and in this central region, we saw that the divergence of the energy flux, was essentially zero. This came from the numerical simulations of Matai and Nakanishi. So we're going to make you, so when the divergence of the energy flux is zero, then the energy equation has a very simple form. It just balances the rate at which the shear stress is working against the strain rate to the rate at which collisions are dissipating energy. So that's what I mean by the algebraic balance of the energy equation. So we use the algebraic balance to determine the temperature. That's one thing we can do. And here, I guess I go through the process by which we do it. That is, you substitute in the constitutive relations for S and gamma and manipulate them a little bit. And one thing that comes out is a relationship between the stress ratio and this function G of nu. Oh, and I have to apologize again. Here I'm using lowercase e for an effective coefficient of restitution. So we make use of the effective coefficient of restitution here in order to be as realistic as possible about the particle interactions.
Now, y is across lateral to the flow or perpendicular? The coordinate y is depth-wise.
Say what?
The coordinate y,
Yes?
that is depth-wise. Y to the depth. And the picture that you showed was three-dimensional, so I was wondering, and you have mentioned
Yes, okay, y is through the depth. So we're tacitly going to assume that things are uniform across the flow. We're going to do a one-dimensional analysis.
so how do the effect of the sidewalls come?
I'll show you. So we kind of spread the sidewalls out across the flow. Okay, so I guess the first step is to eliminate the temperature or express the temperature in terms of known quantities. And let's see, so that's the energy equation. Now here the momentum equation. So we put it, so this is the gravitational term and dealing with the shear stress. So what we do is we take the wall friction, yeah, and spread it out over the thickness of the flow. So that the wall friction, of course, is acting at the walls, but we're taking this and imagining it to be spread evenly across the flow so we can do the simple one-dimensional analysis. Oh, pardon me?
Using P rather than normal stress.
Yeah, P is the pressure is the normal stress. We're not making a distinction between. Okay, and what else? So now I'm going to I'll introduce some boundary conditions. So at y equals 0, so now so now I'm moving over a particle bed. So let me indicate that by. So at y equals 0, I'm assuming that the stress ratio is equal to a yield value that characterizes whether the bed becomes mobilized or not. So that's that condition. And using that condition, I can integrate for S. I can combine these two equations if you like, and have a S as a function of pressure. I can integrate that equation. So I have S as a function of pressure, and of course pressure is a known function of y. S as a function of pressure parameterized by the pressure at the base, and including this yield value of the stress ratio. So here's the yield value of the stress ratio, pressure at the bed, the pressure through the flow, function of y, angle of inclination, and the influence of the walls dealing or involving the width of the cell. So this is where the width of the cell enters into the analysis. At the top of the flow, we take the pressure to be equal to 0, so that gives us the unsurprising determination for the pressure at the bottom of the flow. Okay, that's good. Let me say this, so we're dealing with this additional length scale, L, and L is determined in terms of quantities that appear in this inequality, and this inequality is giving the angles of inclination below which L is greater than 1 diameter. Okay, so we'll see that has some significance in interpreting the data. So that this theory that we're employing is really only valid when L is greater than the diameter of the particles. Okay, what else? And if we take the shear stress to be equal 0 at the top of the flow, then the condition we get from this is a relationship between the yield stress, the tangent of the angle of inclination, the wall friction, and the height of the flow in terms of wall separation. So what we do, so one thing that we predict immediately is the depth of the flow given these parameters. That's one thing that they measured. Okay, and I'm not going to show a comparison between the predicted value of the height of the flow and what they measured, but we do pretty well on that. I'll show you the prediction of Q versus the angle of inclination. Okay, in order to get that, we have to look at our velocity relation. That's just the inverse of the constitutive relation for S, and we're going to eliminate the temperature from that using the relationship that we had from the energy equation. So we've got this relationship that we use there, and let's see. And then we can integrate the result, although, where am I? We can integrate the result there, although this value of G appears in the differential equation for U, and we're going to and that would make it impossible to integrate analytically. So we're going to replace the volume fraction dependence by inverting and relating the G to the stress rate, average stress ratio, and the average stress ratio is related to the tangent of the angle of inclination and the wall shearing. Okay, so what we have here is an expression that comes from an integration of the expression for the shear rate that is then averaged through the depth of the flow. And what we're interested in is this dimensionless expression for the mass flux or volume flux, and that's given by an estimate of the average volume fraction in the flow, the depth of the expression for the depth of the flow, and this expression for the depth averaged velocity. Okay, so that's what I'll show you on the next transparency. Okay, so here's for three different values of the width. Here are the predictions of that theory. All of them start at a yield stress of 0.39. So the yield is the same, of course, for every branch. I've taken the effective coefficient of restitution to be 0.6. There was a parameter that was involved in the determination of L that I take to be 0.5, using a previous formulation that we talked about for L. And the wall friction I take to be 0.25. I mean, if you like, you could regard all of these as being free parameters that I'm choosing, but I'm choosing them, or they're determined in ways that are very close to what anyone familiar with this system would take. And the resulting predictions are the red lines. And the red lines are excellent. Each red line has been terminated when the value of L equals the diameter of a particle, when L over D is equal to 1. So beyond that, this dense algebraic theory doesn't apply. Okay? But we're doing pretty well. Also, it's interesting to think about these points. So these points are points of a flow to which the dense theory doesn't apply. And we're going to talk about that situation next. Okay, so let's see. Yeah, so and here I say for E equal 0.60, this relationship determines the value of the tangent of phi, and that value of tangent of phi is 0.58, and that's about here. It's about at the point where these guys deviate from the prediction. And the reason that they're deviating is because this dense theory doesn't apply anymore, and we have to go back to the previous theory, which involved the divergence of the energy flux. It's a more complicated theory, okay? And the last example I'm going to talk about is an indication of how trying to put together the two theories works. And this is another set of experiments on incline flow where you're in a rotating drum. And as a consequence of the drum rotating, the particles move up the side and avalanche down the face of the drum. And through the window, you measure the depth of the flow, you measure the volume fraction, you measure the angle of inclination of the free surface. And this was done for a variety of cylinder diameters and a variety of cell widths and a variety of angular velocities, all with the cell half filled with B diameters over the range indicated. Okay, so very large parameter space. And the way we deal with this flow is for the bottom of the flow, or we permit the possibility of there being two regimes. A dense regime, or a very dense regime, in which we can solve the algebraic form of the energy balance, eliminate the temperature, and solve as we did for the JOP flow. But this part of the flow has above it what we call a more diffuse flow. Diffuse because we now have to take into account the divergence of the energy flux in the energy equation, and we have to solve a true boundary value problem for the flow on the top. So that's what we attempt in this instance, and I should say that this flow caused some concern for those who had adopted the mu-I rheology, because the mu-I rheology could not predict what they saw. And that was because there was in our view, but I think it's well borne out, in our view that the flow was of a completely different type in a part of the particle flow. Okay, so here's what we got by combining the analysis of the two types of flow. So here's a prediction of a simple mu-I rheology in this case. It captures some of the flow, but by no means does it capture all the flow. But if you combine the very dense analysis, a very dissipative analysis, and a more diffuse analysis, then you manage to collapse you predict all of the data and the appropriate way that it ought to be collapsed.
What is the diffuse layer on top?
Pardon me?
What do you mean by diffuse layer above the dense?
I mean a layer where we have to take into account the divergence of the energy flux in the energy balance and solve a full boundary value problem from the top of the dense flow, very dense flow, to the free surface.
So just below the free surface you have a diffuse layer.
Yeah, but you can really ignore that in this context.
Right. So you have a dense flow which has a free surface and a erodible base.
Yes, that's exactly the boundary value problem we're solving.
So you can ignore the diffuse layer. Cannot ignore.
Well, maybe diffuse is a wrong word for me to use. Why do we say diffuse? Because this, people often talk about this as a diffusion of energy. But you're right. Typically, you've got let's draw a volume. So the volume fraction profile looks something like this. Okay, so and then, so there may be, well, in fact, we solve the full equations here. We're not restricting ourselves to the dense version of the kinetic theory equations. If we're going to solve them numerically, we can solve the full equations. So
I was wondering whether you could take the dense version and just chop it off at the free surface on the top.
well, the problem is that there's a continuous diminishing of the volume fraction here.
How serious is that in terms of data?
I don't know. We didn't bother because we could solve the full problem numerically.
And how do you take care of the bottom? You showed some conditions for the erodible base. Those are the conditions you use at the bottom.
Here yes, that is, yes, exactly. This analysis proceeds as we did before. And and then we employ, I said much earlier that we have boundary conditions for the full set of equations at an erodible bed.
Erodible bed is what it is.
Yeah, so we know what that boundary condition is, both for so we take this at the surface of an erodible bed, we take the slip velocity to be 0, and we take the energy, the erodible bed dissipates energy. It accepts energy, it doesn't create it. So we have a set of boundary conditions and a set of differential equations. and we can solve them. We solve them numerically, if you like, or some other crude way. So here, I think we solve them both numerically, and talk about crude ways. We use the trapezoidal rule simply to integrate a system of first order equations. So once again, we're not predicting profiles through here. We're predicting average quantities averaged through the flow. And of course, the scaling comes out as part of the formulation of the problem, really.
So the mu I fails because it can't take care of the bottom condition? Or?
No, fails because it can't describe well the less dense layer above the more dense layer. It can't describe this layer. So if you like, you're in this instance, so let's talk about mu I. So mu I, so the question is, how large a value of I can you push the mu I, okay? And it turns out that, I don't know what it is, maybe it's 0.2, let's say. I'll be charitable. And then beyond that, think the mu I rheology doesn't agree with what's observed, and because what's observed here is a truly collisional flow that depends upon coefficients of restitution, and so the mu I rheology breaks down at large values of I. That's what we're seeing here.
So, okay, I thought that they couldn't handle the erodible base.
I mean, they don't. Are we talking about Cameron's version, or are we talking about the original version? This is simply applying the homogeneous, steady, original version of the mu I rheology with a single parameter. Okay, so earlier when the mu I rheology was introduced to this group, there was a version of it that involved 3 parameters, but that wouldn't do it here. Okay.
So Cameron has a version with erodible base.
Cameron has a version that works for inhomogeneous situations. I mean, I don't know that he's applied it to an erodible bed. He typically is applying it to situations with rigid, bumpy bed. Yeah, exactly. Okay. Where am I?
Could I try to rephrase something?
Yeah.
So, in other words, if I'm following you, then you were recasting the mu I in terms of the temperature, giving you the length scale. Then, and since that connects to normal rapid granular flow, and the whole range of I.
Well, up to the point where force chains are playing a dominant role.
You can extend to the dilute regions, the large I.
Oh yeah, we can. Yeah, that's no problem. Yeah, but we can't take it beyond.
Cast it into the temperature perspective, and that has a natural way in terms of the rapid granular flow, dilute stuff. That's a natural structure for that.
Yeah,
Connect properly to that limit.
that's right. We understand how to go from force chain spanning the cell to. But what do you think about situations in which force chains span the cell? Can you talk about a rheological relation there?
Technically, if you're, as a rheologist, you wouldn't.
You wouldn't.
No.
Yeah, I agree. Yeah.
So, and not that they're not important, but from a rheological perspective, then your length scale is the same size of the apparatus. So
Exactly, and your rheology is dependent perhaps on the walls of the apparatus.
it's not called rheology.
Yeah.
The whole point of that was to not have apparatus-dependent material properties.
Okay, so I suspect that some of the work that's been done on dense suspensions involves the walls in a very significant way.
Absolutely.
Okay. All right, well, that's the end of this particular session. What are the... Okay, so the conclusions here is we do pretty well in reproducing the experiments of JOP and understand perhaps how the mu I rheology fails when there is a less dense layer upon a dense regime. Thank you.